All right, folks, happy Wednesday. So for the sake of time, I'm not going to read the announcements on Canvas, but there is one posted about the exam 1 information. So please read that. Let me know if you have any questions, but I would read that earlier rather than later. So like right before you decide to take the test is probably not the best time to read that, but just go ahead and make sure that you read through that. Let me know if you have any questions about that, and then yeah, that's that. I know there were a bunch of folks in office hours today, so thank you so much for coming and asking questions. I feel like there's definitely some confusion out there, especially around like the sign and, not the sign, but the tangent stuff. And so what we're gonna do is take a look at one quick thing from Monday's work. Okay. So before we take a look at 5.3, which is on the menu for today, we're going to take a look at the 5.2 one chart that I think is super, super helpful. Okay. Okay. So this is sort of the very last part that we did in class on Monday, but we talked about the inverse trig functions. And so I just want to be really clear about something here, which is that every single column here represents a different sort of class of trig function. So we have like our basic trig function, which we call our main trig function. And we know those are sine and cosine and tangent, okay? And so when someone says 3 main trig functions, you're thinking sine, cosine, tangent. You want to know that sine is not just opposite over hypotenuse, but that sine is also the y coordinate on the unit circle, okay? So the y coordinate is sine, the x coordinate is your cosine, and your tangent is your y over x, okay? So I feel like that's a part that folks know pretty well. But before I talk about the other trig functions, are there any questions about the 3 main trig functions? Okay, so are people's concerns more about the reciprocal versus the inverse trig functions? That's what I'm guessing is true, but yes, okay. So when we first learned about the reciprocal trig functions, okay, the reciprocal trig functions, we learned about them without this inverse trig function there at all. And that was on purpose, okay? So when we think about the reciprocal, what we mean is we do 1 over something, okay? So for example, 1 over sine theta equals cosecant theta. Like that's what we're doing when we say reciprocal, okay? That's how we get cosecant is 1 over y, okay? And if we do the same thing with cosine, 1 over cosine theta equals secant theta. And so that means that secant theta is just our 1 over x value, okay? And then we could take a look at tangent and say 1 over tangent theta equals cotangent theta. And all that means is that cotangent is not y over x, but it's x over y, okay? So let me pause here for a moment. I'm going to ask you to ignore that first column that says inverse trig functions. How do we feel about the main versus the reciprocal trig function? Okay. So now this part, I do want to make clear that these two right here, these two columns, the main trig functions as well as the reciprocal trig functions, your answer should come from the coordinates, okay? And we can think about those being on the outside of the unit circle. So your answer should be an x value, a y value, or some combination of x and y, like 1 over y, or 1 over x, or y over x, or x over y. Your answers are coming from the coordinates that are outside of the unit circle, okay? Now, I think when we only knew the main and the reciprocal trig functions, well, that was totally fine. Like it wasn't a big deal because all we were doing was finding the coordinates from the outside. But what we have here with the inverse trig functions, which sort of now we need to be more careful about our inverse. The inverse means that all of our answers should be angles. That means that all of our answers should come from the inside of the unit circle, okay? So for example, if I'm looking for inverse sine, that means I'm given like some coordinate and I want to find the angle that goes with that coordinate. And same thing with the inverse cosine. I'm given a coordinate and I want to find the angle that matches with that coordinate. And if I'm given the inverse tangent, I'm looking for the angle that goes with the coordinate I'm asked for. And so maybe underneath where it says inverse trig, we could say that our answers are angles, or that they come from the inside of the unit circle, okay? So that's a really important distinction to make in your brain. Am I looking for a coordinate or am I looking for an angle? And if you're thinking, well, I really wish there was like a tell symbol, like how do I know I'm looking for an angle? Every time you see this little -1, you're looking for an angle. Okay. So let me pause here for a moment, give you a little bit of time to digest what I just said, okay? Main trig functions and reciprocal trig functions, your answers are coordinates. But your inverse trig functions, your answers are angles, okay? Do we want to do a couple problems to kind of practice the difference between those? Would that help people feel more confident whether they get it or not? Yes. Okay. All right. Okay. So let's do this. Before you tell me your answer, is my answer a coordinate or an angle? Okay, your answer is a coordinate. Is my answer a coordinate or an angle? It's an angle, right? There's that tell, that -1 is like, hey, pick an angle. And then when there's no -1, you're looking for the coordinate, okay? So for the first one I wrote down, sine of pi over 4, I want to find the y value at pi over 4. And when I look at my unit circle, I get √2 over 2. Okay. Now this middle part, you'll probably never see in a textbook. They're kind of terrible like that. This is what they write. They're like sine of pi over 4 equals √2 over 2. And you're like, well, how did they get there? This is how. Okay, they were looking for the y value at that angle. Now, if we look at the second problem, okay, that -1 means we're looking for an angle. We want to look for the angle with a y value of 1/2. So like they give you the y value. They're like, hey, a y value of 1/2, go on your unit circle, find out where those angles are. And when you look at your unit circle, you should see that pi over 6 is one of those angles, okay? And the other angle is 5 pi over 6, okay? Thumbs up, thumbs down. I know we probably want to try some tangent stuff, but how do we feel about the sine here? Okay. Let's do tangent. So let's say tangent of 3 pi. We'll pick one that you guys want to do. Pi over 6, okay? So tangent of pi over 6. That means my answer is an x over y value at pi over 6, okay? So we go to our angle. We notice the y value is 1/2. We know that the x value is √3 over 2. Okay. Now, we can simplify this fraction in a number of ways. So one way that I like to do it is just like 1/2 times the reciprocal of the bottom, right? That's what we did in class the other day. And we can reduce the 2 and the 2, and we get 1 over √3. Okay. And then I was like, oh, it's important to know that this is the same as √3 over 3, right? So I don't really care which one you use. I care that you know that they're equal to each other. But I heard that Val talked about something called the sandwich method, and I just want to kind of show us that it's the same thing. So if you like the sandwich method for reducing fractions and you want to use it, on the exam, that's totally fair, okay? So if we think about the sandwich method, all we're doing is like imagining our fraction as like parts of a sandwich, okay? And so what I mean by that is if we were to break this down, this 1 would be like the bread, and then this 2 on the bottom would be like the bread, right? And then the insides of your sandwich could be whatever you like, peanut butter and jelly, turkey and avocado, okay? But the 2 and the √3 are sort of the fillings in your sandwich, okay? And so it turns out that we could sort of do this like multiply by the reciprocal, ooh, like a chunky strawberry jam. That sounds delicious. Okay, so if we take this and we take the bread pieces and smash them together, we get 1 times 2, okay? So this 1 is this 1, and this 2 is this 2. So we took our bread and we smashed it together. And then we took our fillings and we smashed those together, 2 times root 3. So this 2 and this root 3 are this 2 and this root 3. Okay, so if any of you have been to like a restaurant where they serve an open-faced sandwich, so an open-faced sandwich just means that there's usually no top piece of bread. And so this is like a upside down open-faced sandwich. So you took the bread, you smashed the pieces together. You took the fillings, you smashed them together, and then you just like splat on the plate. Okay? Now, if we look at our numbers here, 1 times 2 on the top, well, this was 1 times 2 on the top when we did it with our multiply by the reciprocal method. And when we did our multiply by the reciprocal method, we got 2 times root 3. So we're getting the same thing no matter which way we choose to simplify our fractions, right? This 2 and that 2 reduce, and I get 1 over root 3, which is the same thing I got using the multiply by the reciprocal method. Okay? Does that kind of clarify how to use the sandwich method?
Yeah, that clarifies.
Thank you. Okay. Does this clarify how we find the tangent of pi over 6? Like we look at the y over x value. So if I ask the question this way, inverse tangent of root 3 over 3. Oh, where did we get the root 3 over 3? Okay, so I took 1 over root 3, and there's that thing that mathematicians don't like where they're like, ooh, a radical on the bottom, gross, get rid of it. So we get rid of it by multiplying by a fancy way of saying 1. So now root 3 times root 3 gives you 3 on the bottom. And 1 times root 3 gives you root 3 on the top. Okay, so some might call this it's been rationalized, like there's no more square root on the bottom, okay? So some of us are like, great, I got the division part. I know it's 1 over root 3, but why, if you don't care, would I learn how to write it as root 3 over 3? And so this kind of comes up when we're looking at the inverse trig functions, because sometimes people are going to ask you the question this way. Find the angle, right? That -1 means find the angle. So I want to know the angle where when I take the y and I divide it by the x and I simplify it, I get root 3 over 3. Okay. So I'm looking for the angle where the y over x, and I've already reduced it, is root 3 over 3. And so you could spend all day looking for coordinates on the unit circle, and you're never going to find a coordinate of root 3 over 3. So that's where it's important that we kind of know how to go backwards, like where did that come from, okay? And so as it turns out, we can sort of use the other side to help us go backwards. We can say that this is really saying the inverse tangent of 1/2 over √3/2. Right? We just showed on the other side that 1/2 divided by √3/2 is 1/√3. And so now this becomes a little bit easier to find coordinates on the unit circle. We're looking for the y value of 1/2, and we're looking for an x value of √3/2. Okay. And so if we look at our unit circle, we'll find out that one option is pi/6. Or what's another option that if I reduce, I still get a positive √3/3? Right? Where is that other angle? That if I simplify,
Wouldn't it be in the fourth quadrant, negative √3/2, comma, negative 1/2?
I take the coordinate and let's change that to quadrant 3.
Quadrant 3, 1, 2. Yeah, quadrant 3.
That should be 7 pi/6, yeah?
Yeah.
Yep, exactly. So you could have like a positive divided by a positive, or another way to get a positive number is if I have a negative divided by a negative. So like this one came from the inverse tangent of a negative 1/2 divided by a negative √3/2. Okay. But the result, I still get a positive value at the end. And so it still answers the question. Okay. Now, I've heard a lot of questions about, but can I just leave it as 1/√3? So let's say on the exam you have this question, tangent of pi/6, and you tell me the answer is 1/√3. Okay? That's totally fine. I will give you credit for that. I have no problems if you don't rationalize the bottom. Okay? What I do have a problem with is if you write down this and you're like, I'm just too lazy to rationalize it, but I know how to do it. Like, that's fine. But if you don't know, like, or you don't feel comfortable going between the two forms, then I would encourage you to practice rationalizing, like writing both of those. Okay. So it's kind of you do what you need to do and be honest with yourself. Are you leaving it as 1/√3 because you're just feeling a little lazy, which is fine. We all have those days and I'm fine with that. Or are you leaving it there because you don't know how to get to the next step? Okay. Because if you can't get to the next step, then a question like this arc or this inverse tan one becomes really hard. Okay. All right. So it's like, I want you to know how to use it. If you feel comfortable with that, I'm good with that. But if you don't know how to use it, I would encourage you to practice this as much as you can, like during this section. Okay. Would we like to do one more problem? Would that be helpful? Okay. I'm going to do like a cotangent one. Okay. All right. So let's say we have cotangent. And if I'm going to write the problem, what should I put in here? Like, do I want to put an angle in there or do I want to put a coordinate in there? Okay, so I am going to give you an angle, which means that your answer better be a coordinate. Does that make sense? If I give you an angle, you better give me a coordinate. But if I give you a coordinate, then you better give me an angle. Okay. So let's see. Pick an angle. Somebody pick an angle on the unit circle, or not on the unit circle. Let's see what we can do in terms of making up problems. All right, we got a 4 pi over 3. 4 pi over 3. Okay, so once I go to 4 pi over 3, I want to find the x over y value at 4 pi over 3. That's literally what I'm looking for, okay? All right, so we know we're gonna need a fraction line, right? Because I have a x value on the top and the y value on the bottom. So when I go to 4 pi over 3, the x value is a -1/2, okay? So the x value at that angle is a -1/2. The y value at that angle is -√3/2. All right. If you are feeling like, oh, I don't know how to simplify, so maybe I should just not answer a question at all, like I would encourage you to write out this part, okay? This right here demonstrates a really important piece of like conceptual understanding, that you get what the question is asking. The rest of it, in terms of simplification, well, that's like a different skill, right? Do we want to see the multiply by the reciprocal, or do we want to see the sandwich method? Or both? What would we like?
Both.
Both, okay. So we get -1/2 times -√3/2. Whoops, I didn't flip it. We want to make sure we flip that second one. So 2/√3. And I can reduce those here. Is the sign of my answer going to be positive or negative?
Positive?
It's going to be positive, yeah, because I have a negative and a negative. So I know it's going to be positive. And so I get 1/√3. Or we know that's equivalent to √3/3. Okay? No worries. Sometimes I miss those times too. Okay, now if we're going to try the sandwich method, let me rewrite the fraction. Sometimes with there's a negative sign, I usually pick whether I want the negative sign with the top or the bottom. So I'm going to write -1/2 as -1/2. Okay? And I'm going to do the same thing with the bottom. I'm going to have -√3/2. And so when I think about my sandwich, I know I want to find the bread. So -1 and 2. I'm going to smash those together. So -1 times 2 will make the new numerator. And then I'm going to take my chunky strawberry jam, or whatever it might be, 2 times -√3. And multiply those, or smash them together, to make the new denominator. And it's probably good practice to kind of reduce as we go. So those 2's reduce, and I'm left with a -1/√3. And we know that's the same as 1/√3, or √3/3. Okay? So two different methods, sort of, to get to the same answer. Okay? All right, if I were going to write a question that was saying, hey, now I want you to find the angle, all right, how would I start to write this question? Like, I want my answer to be an angle. What does the question actually look like? Yeah, exactly. I have that -1, right? The tell. That -1 is telling me, oh shoot, your answer better be an angle. Now, what does that mean for like this part of the problem? Do I put an angle in here? What do I put in there? Or what could I put in? Yeah, I put some coordinate, okay? Now I put a coordinate, but when I'm thinking about the coordinate I put in here, I can't just put an X coordinate. I can't just put a Y coordinate. I would have to do an X divided by Y. Why is it that I need an X divided by Y? Like, how come I can't just put like a 1/2 in there or √2/2? Like, why is that wrong?
Because you're just putting one X or one Y, they're basically smashed together.
Yeah, they are smashed together, but what part of this problem tells me that I want an X over Y?
The cotangent.
Yeah, exactly. This cotangent means the coordinate that's in there has to be the X divided by the Y. Or we could think about it like the reciprocal of tangent, okay? So again, a lot of times when we ask these questions, they've already been simplified. Like, they're not going to be kind and give us something like that that's not simplified. That would be really easy for us to find. What we need to do is when they give us something like this or something like this, can we unsimplify it to figure out where it came from? Okay. So let's say we had this. √3, okay? That came from somewhere. It came from some X divided by Y, but they already simplified it. So in order to answer the question, we got to think, where did it come from? Okay. And so our question is, all right, what do I divide by what to get √3 after I simplify? And so if I think about this, when I had the 1/2 on the top, I got a 1 over √3. So if I want to get just a regular √3 out, maybe I should put the √3 one on top. And if we use the sandwich method here, bread, chunky strawberry, well, yeah, that gives us √3. Okay, so now we know where it came from. It came from some angle that has an X coordinate of √3/2 and a Y coordinate of 1/2. Right? Where do we find that angle that has an X coordinate of √3/2 and a Y value of 1/2? Well, I believe that pi/6 fulfills that requirement. Okay. Or the other one that fulfills that is when I have both of them being negative, because when I divide a negative by a negative, I get a positive. Okay. Let me zoom out for a moment so we can kind of take a look at this sort of extra piece of work that we did here. All right, put it all on one screen for you. Are we feeling maybe a little bit more confident about how to use the unit circle? Or more confused? Which direction did that go? Okay. Okay. The nice thing about this is you guys can make up your own problems pretty easily. And I think if you practice making your own problems, then that actually helps you understand how to read the questions, okay? So knowing like if I have the -1, my answer is going to be an angle, that means the information I'm given is a coordinate, right? Or the other way around. If I'm asking for a coordinate, then I better know where the angle is. All right. So let's do this. Let's start a little bit of 5.3, which actually should be kind of review from this quiz 3 that you all turned in, okay? But what might be valuable for us here, that's the quiz. What might be valuable for us here, again, before we go there, is this chart right here, right? We've practiced in 5.2, we practiced the pink column, the inverse trig, and we practiced the green column, the main trig function. The orange column, we'll get a chance to practice right now. Okay, so like what happens when we're looking for the reciprocal? But the thing to keep in mind here is if there's no -1, you are not looking for an angle. Okay, if there's no little -1, you are not looking for an angle, and your answer should be some sort of coordinate. Okay. Okay, so okay, so let's actually jump right into these questions and just kind of see. So for example 1 here, I have the secant of pi/3. Okay, so what angle am I going to go to?
Pi/3.
Pi/3, exactly. So at the angle pi/3, okay, and I sort of get this because that's the angle we're given in the problem. Now, once I get to that angle, what am I looking for? Like the x value, the y value, the y/x, like what are we looking for?
Would be the y value.
How'd you get that?
The way I have it in my head is like, so sine y, cosine x, secant y, cosecant x. That's just, I have that memorized.
So sine, cosine, tangent, yeah. And then the
So
reciprocal
just,
line is cosecant.
oh, so that's my bad.
Yeah. The reciprocal of cosine is secant.
Okay, so it'd be x then.
Yeah, so we're looking, because it says secant, okay, because this part says secant, what we're looking for is the 1/x value. Okay, so at the angle pi/3, we're looking for the 1/x value. And it's the 1/x value because it's the reciprocal of cosine. So now that we know what we're looking for, we go to pi/3, we find the x value, and that should be 1/2. So I want the reciprocal of 1/2, which is just 2. If we wanted to write this out, we might say reciprocal of And that will give us so let's kind of practice the same thing with example number 2, okay? So where am I going on my unit? Like what angle are we looking for?
5 pi over 4.
Yeah. So this angle right here, I'm counting in the negative direction, but it's the same thing as finding secant of 5 pi over 4. Okay. And so I'm going to 5 pi over 4, and I'm looking for secant. And from example 1, we know that's the 1 over x value. Okay. So what I'm looking for is the reciprocal of, let's see, the x value there is negative root 2 over 2. And so that reciprocal is just negative 2 over root 2. Okay. And so that x value, the reciprocal of that x value should be negative 2 over root 2. Okay. I do want to talk about how to rationalize this, but before we do that, are there any questions about example 1 and example 2? I did notice a question in the chat about, are we allowed to put the unit circle on your reference sheet? 100% you are allowed to do that. Yep. So it's really up to you. I think at this point, if you're gonna do it might be nice to have the whole unit circle on there, and maybe a goal for yourself is by the end of the semester, we're really down to just that first quadrant, okay? But I think it's definitely a little bit different in sort of this online learning platform than it might be in like a regular classroom, okay? Cool. I think the unit circle is a good thing to put on there. That chart that we talked about in 5.2 is probably also a good one to put on there, okay? So those you could definitely shrink down to make a little bit smaller, but I think they'll help you remember how things work. Okay. So one of the things is you might not see negative 2 over root 2 as an answer, okay? Because again, that rationalization of the bottom. So if we think about getting rid of that square root on the bottom, we could multiply by square root of 2 and square root of 2, right? And so this is going to give me negative 2 root 2 on the top. And what do I get on the bottom here? We get a 2. Good. And we could leave our answer like this, or I think it's just one small step to say, oh, we got a 2 and a 2. Those are going to reduce. And so maybe a more textbook acceptable answer might be negative square root of 2. Okay. Now, I will say this, like, I know I write out a lot how we get from one to the other. The reason why I write them out like this is because I've seen a lot of students try and just memorize them instead of understanding them. And then what happens is sometimes they memorize the wrong thing, where they don't know how to show their steps to get from one to the other. And if you simplify wrong, that could lead you to more wrong answers, right? So even though we're working with a lot of radicals and a lot of fractions, like that's part of what makes this like a student successful in this particular unit, okay? So if it's making you kind of nervous, like that's okay, but you got to embrace it, okay? All right. So let's take a look at some of these other ones. We've got cotangent of 13 pi over 6. Okay, and let's see, how do we find an answer to this question? Like, what is it asking for? What information do they tell us?
I was gonna say, because we know that tangent is y over x, then we know that cotangent is x over y.
Beautiful. So the cotangent tells us the y over x. Good. What other information do we have here?
Got the angle.
We got the angle, right? We know there's 13 pi over 6, but you might be looking at your unit circle being like, well, crap, there's still 13 pi over 6, right?
Pi over 6.
Yeah, so that's going to be the same thing as pi over 6. Right? So you can think about this question as the same as cotangent of pi over 6. So let's do our work off to the side. We're going to go to pi over 6. The x value is root 3 over 2. And the y value is 1/2. And we can take our bread pieces and smash them together. We could take our insides of our sandwich and smash them together. And we could reduce. And so we get root 3. Okay? And so that's how we get our answer of root 3. All right. How are we doing out there? Making a little bit more sense, like that difference between the inverse and the reciprocal? Good so far. Okay. So let's just talk quickly through these next 3. So example 4, 5, and 6, and then we'll kind of pick, we can make up our own problems for 7 and 8. All right, so kind of get that practice in terms of making up our own questions. All right, so cotangent of 5 pi over 4 means that I'm going to go to 5 pi over 4, and when I get there, I'm going to find the x over y value. So I'm going to go to 5 pi over 4. I'm going to find the x over y value. So the x value at 5 pi over 4 is negative root 2 over 2, and the y value is also negative root 2 over 2. And so when I reduce those, I'll get a value of 1. Okay. And I could do the sandwich method here, but I think what maybe is a little bit more clever is you notice that the whole numerator is equal to the whole denominator. And so when the top equals the bottom, we know that that simplifies to 1. Okay? Fast math, yeah. All right, so cosecant at negative pi over 3. Well, I know negative pi over 3 is the same as 5 pi over 3. Okay. And when I get there, because I'm looking for cosecant, remember cosecant is paired with sine, I'm looking for the 1 over y value. So I want the reciprocal of, let's see, the y value there is negative root 3 over 2. Okay. Is my answer going to be positive or negative?
Since 1 is positive and y is negative, then it'll be a negative value.
Yeah. So we don't change the sign of it. We just take the top and bottom of the fraction and we find the reciprocal. Okay, so the reciprocal here doesn't mean we change the sign. It just means we flip the top and bottom. Okay. So on an exam, you can totally leave your answer like this. I'm fine with that. I'm fine with that as long as you know it's the same as negative 2 root 3 over 3. Okay. And this is an in case someone asks you to go backwards and they give you the rationalized form, can you unrationalize it to get to your answer? Okay. All right. So at the angle, we're looking at the angle of 0. Okay. We're looking at the angle of 0, and when we get there, we want to find the 1 over y value. Good question. How would you unrationalize it? Like if I saw this and I was looking to unrationalize it, I would think I know this numerator stays, but another way I could write 3 is root 3 times root 3. So it kind of varies by the problem, but you want to match it with something that is sort of like extra on the top. Okay. Good question. Okay, so at the angle 0, the 1 over y value. So we're looking at the y value of 0. So the reciprocal, what is the y value of 0?
0.
0. So we're looking for the reciprocal of 0.
1 over 0.
1 over 0, and we call that
Undefined.
undefined. Okay. So sometimes it's okay for things to be undefined, and we'll kind of see what that looks like on the graphs when we get to that next week. Okay. All right. So let's take a look at making up a couple of our own problems, okay? So which function of the secant, cosecant, cotangent would we like to practice? Well, we already got one, okay. Cotangent of 20 pi over 3. All right. So 20 pi over 3 seems real big, like more than one time around the unit circle. So it would probably be valuable to us to find the coterminal angle, right? How do we find the coterminal angle from 20 pi over 3? Right, so this is a good review from 5.1. How do we find that coterminal angle? We subtract 2 pi. And since I have a denominator of 3, maybe I could call 2 pi 6 pi over 3, right? And if I do that one time, I get 14 pi over 3. So let's do it again. We get 7 pi over 3. We do it again, we get pi over 3. Okay, so we're really saying, let's go to pi over 3. And pi over 3, once we get there, we're looking for the x over y value. Okay. And so I go to pi over 3. I know the x value there is 1/2. I know that the y value there is root 3 over 2. And if I use my sandwich method, (1 over root 3 or root 3 over 3. What? Oh my gosh, I can't even subtract this morning. 8 pi over 3, 2 pi over 3. We changed the x value to a negative, right? Negative, negative, negative. That's the benefit of showing all your work. You could just go back and just plug in that negative sign where you need it. All right, so we get a final answer of negative 1 over root 3 or negative root 3 over 3. Okay. All right, let's pick one more problem. Which one are folks feeling like they would like more practice with? Cosecant, secant, cotangent? Cotangent, all right. Yeah, that is the one. Okay, so cotangent. Anyone have an angle in mind that they'd like to try? Maybe let's try 3 pi over 2. Okay, sometimes we ignore the quadrantal angles, but they're equally important. So let's go to 3 pi over 2, and let's find the y over x value. Yeah. And so we go to 3 pi over 2. What's that x value and what's that y value? Yeah, we got a 0 over negative 1. Now, believe it or not, this is probably like not this particular problem, but like 0 divided by something versus something divided by 0 is probably something I would get on that reference sheet, right? So I hope we know when we have 0 on the top and a number on the bottom, we get 0. Okay, so cotangent of 3 pi over 2 should be 0. But again, it might be nice on your reference sheet to write like 0 divided by a number equals 0. But a number divided by 0 equals undefined. Right? These are sort of the small things that are sometimes the difference between fully getting a question and like almost getting a question. And so even though it's not necessarily a topic in the book, it might be helpful to getting you to make sure you feel confident about that, you know, like on an exam. Okay. All right. So we feeling better than we felt working on that quiz 3? Yes. I know there were a lot of good conversations happening around them. But I think the most important thing is to remember the difference between a reciprocal and an inverse. Okay. All right. So let's do this. Let's pause here. Let's take a break. And when we come back, we'll take a look at the rest of 5.3. Okay. I'm going to stop sharing my screen. Okay. Thank you. Perfect timing. Perfect timing. Thank you. Okay. So a couple things. I feel like my not totally great lessons last week, I feel like we're not feeling ready for this test tomorrow. Would it be okay if we bumped the exam? Or are people like, we want to take it tomorrow?
I kind of missed the instructions in regards to the reference chart. Is there somewhere I can look back to, if it's in previous recordings or whatever, for that reference chart?
Yeah, so for the reference sheet, the short of it is you can have like a regular sized piece of paper whatever formulas, examples, charts, all that stuff. Whatever you want to put on there would be totally fine.
Awesome.
No restrictions on it, except that it can't be more than one sheet of paper.
Okay. Now, is that single-sided or front and back?
Single-sided.
Okay. Yeah, my hang-up is just figuring out the main trig functions, or the 6 trig functions, and the unit circle. I think I got a pretty good handle on everything else until I find out that I did something wrong. But so far, I think I just overcomplicate things is my problem.
Okay, that's good. That's good. Okay, let me pull up the course schedule so we can just kind of take a look at this together and maybe figure out when would be a good time to reschedule. Okay, so can you all see that screen? Yeah, it's the course schedule. Okay, so okay, let's back end this a little bit. I know for those of you who were in Math 116, we had our back-to-back final and our exam 4, okay? I do want to make one adjustment to that, which is the final exam is actually going to be optional. In the sense that it still holds that if you bomb an exam, your final exam, your final exam can replace your lowest test grade. Man, I don't even have the faces pulled up right now. Okay. Okay, so your final exam is optional, meaning if you take exam 4, and I will make sure the exam 4s are graded pretty quickly so you can make a good decision for yourself. But let's say you walk out of all 4 exams and you're like, I got an A. Like, you can take your A, peace out, have a great winter break, okay? But with your exam 4, if you're like, oh, you know, there was some exam during the semester that you didn't feel good about, then you can take your final exam and that will replace your lowest exam grade, okay? So knowing that, we sort of have that last exam the last Wednesday of class. If you take the final exam, then it either counts as a grade or I don't know, I hadn't thought that far. What if we take the final exam and do poorly on it? I don't know, let me get back to you on that. Trick question. Okay, that's fair, that's fair. I don't want anyone to like just like take it to take it, mostly because I don't want to grade it. So if you want to take it, then take it to take it. Otherwise, I don't really want to grade things if it didn't go well. Okay, so exam 4, we could potentially bump to like, we could still have that day as class, is what I'm saying, okay? This final exam, technically our last day of class is Monday, December 14th. So that final exam could even be bumped to that Monday. So you would have sort of a weekend to kind of decide whether you wanted to take it or not. That would free up that day. So we have this exam. If we bumped exam 4 to like that Thursday, then in theory, we could also bump this exam 3 a couple days, and that would be okay. And then exam 2 could also be bumped like a couple days, so that we're almost doing like every other week as an exam, rather than like some weeks feeling like they go too quickly. It's optional, so if you drop a grade, then we pretend it never happened. I mean, you could eat cookies while you're taking the exam. I don't care. But it's probably hard to do something like baking cookies while you are taking an exam. Okay. Okay, so if we moved exam 1, which was supposed to be tomorrow, oh, what day is so the 22nd, we could move it to the 23rd. We could also, I heard a few people say no to this, we could bump it to early next week. Kind of up to you. Do we have strong feelings one way or another? 23rd, so like just even one extra day would be helpful. Okay. Okay, cool, let's do that. So exam 1 will be Friday, opens Friday 10. Okay. Yeah, so I think that, Richard, you bring up a good point, right? So if we bumped the exam to like Tuesday of next week, we would have an extra class day to sort of finish up 5.3 and review. So I guess the question is really, do you folks just need extra time to review stuff, or do you want extra like in person? Yeah, I think we're pretty much gonna bump exam 2. I think we could even make that right now. Okay. Uh, 5.4, so we actually switched the order. We did 5.1 and then we did 5.4 last week. So we did 5.2 on Monday and we're doing 5.3 right now. Yeah. So there's not like a whole missing section. It's just a question of how much of 5.3 can we get through in the next hour and 45 minutes or hour and 30 minutes. A lot. Okay. All right.
Now, if you bump the exam back, are you still going to make it available on the 22nd and then just make it due extension date or due date different?
No, it'll just open on Friday at 9:30 and then you'll have a 24-hour window.
Okay.
All right. Maybe this feels a little bit better then to folks, sort of like an every other. Imagine if we still use paper for school. I know. I still use a lot of paper myself, but yeah, I don't miss making copies though. Okay. All right. So it sounds like we've got a plan. So exam 1 will open Friday at 9:30 a.m. But you have 24 hours to kind of do this, and let's see how much of 5.3 we get through, okay? Yes, all of 5.3 will be on this exam, okay? Okay, so let's jump right into it. Okay. So, finding trig functions from other trig functions. So we've kind of seen this before, where I was like, hey, you have this cosine of something and draw a triangle and solve it, or find the trig functions that go with it. And all we're doing in the next example is we're extending what we already know about SOHCAHTOA to all 4 quadrants, okay? So let's unpack what we have. the first thing I like to do with these kinds of problems is I like to identify which quadrant my triangle's in, okay? So let's see what they tell us. They tell us that sine is 3/4, okay? But more significantly, sine is positive, right? Sine is positive 3/4. But they also tell us that cosine is negative. Okay. So my question to you is, which quadrant has a positive sine value and a negative cosine value?
Two.
Mm-hmm. Anybody have any questions about where we got quadrant 2 from?
You're just asking for a negative x and a positive y value, correct?
Yeah, exactly. This is really saying positive y, and this is really saying negative x. Okay? So we've got our quadrant 2. Now we're going to draw our reference triangle. Okay? So we want to draw our reference triangle so that it's in quadrant 2. So if we think about quadrant 2, we don't want to draw a triangle like this, because this would be more like quadrant 1. Okay, so if I want to draw a reference triangle in quadrant 2, it's going to be flipped so that the pointy part is facing to the right instead of to the left. And so when we draw our reference triangle in quadrant 2, then we end up with something like this. Okay, and this is our theta. Exactly. The angle theta should be where the origin is. Exactly, exactly. Okay. And so if we kind of want to imagine the axes, right? Now we can see that this triangle is in quadrant 2. So we're going to draw our reference triangle, and then we're going to label it with the information that we're given. So if I know that sine is 3/4, okay? If I know that sine is 3/4, I can label this vertical side as 3, and I can label the hypotenuse as 4, right? Because sine is opposite over hypotenuse. So I've got opposite of theta is 3, the hypotenuse is 4. All right. Now, in order to find all the trig functions, I'm going to need to know what that adjacent side is. All right. So usually after I draw my reference triangle, I also find the third side. Okay. And we can find that using the Pythagorean theorem. So we know that a squared plus b squared equals c squared. That's going to give us, let's say, x squared plus 3 squared equals 4 squared. And x squared equals, let's see, 16 minus 9 is 7. So x is either plus or minus root 7. Okay. Now, if I'm looking at this distance, all right, I know a distance can't be negative, but I'm facing the negative direction. Like I've moved root 7 units, but in the negative direction. So my adjacent side here is actually negative root 7. right? It's not the special right triangle because we need to label it first. If they give us 3 and 4 as the legs, we're totally good to have 5 as the hypotenuse. But when they tell us the hypotenuse is 4, it's not that 3, 4, 5 triangle anymore, okay? All right, so any questions on finding the quadrant or drawing the reference angle and finding the third side? Because I knew it was in quadrant 2, so if you remember, we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. So you want to draw a triangle that is in quadrant 2. So you want your triangle to be here, okay?
I think they were asking like in regards to how do you know it's going to go to negative x? But yes, so yeah, she's asking that. I'm sorry.
Do you know that cosine was, yes, exactly. Because the cosine is negative, which means I got to be in the negative x direction, and the sine is positive, which means I need to be in the positive y direction. Okay, thanks. Okay, so we found our quadrant, we drew the reference triangle, we found a third side, okay? And so now we get to answer the question, find the remaining 5 trig functions. And so no matter what information they give me, I always set it up so that I have all 6 of them written out. So I got my sine, my cosine, my tangent. I've got my reciprocal of sine, which is cosecant, my reciprocal of cosine, which is secant, and my reciprocal of tangent, which is cotangent. Okay? So I write out all 6 of them just to kind of set the framework for myself. And then they give me sine. I already can say the cosecant is 4 over 3 because all I'm doing is finding the reciprocal, okay? But in order to find the other 4, I need that negative root 7. So my cosine is going to be negative root 7 over 4, right? My adjacent over the hypotenuse. Yeah, exactly, negative root 4 over 7. And then my secant is the reciprocal, negative 4 over root 7, okay? My tangent is negative 3 over root 7, and my cotangent is the reciprocal of that, negative root 7 over 3, okay? So it's a little bit, the added layer is like, can you draw your triangle in the right quadrant so that all of your positive and negatives work out, okay? So question for you folks, how come I didn't make the 3 a negative?
If we look at the quadrants, your y value is like positive, versus being under the x-axis.
Yeah, right? Like the way we drew the picture tells us that 3 needs to be positive, okay? So the way we draw the picture, I think, helps us figure out whether things are positive or negative at the end, all right? All right, so step 1, find your quadrant. Step 2, draw your reference triangle and find your third side. And step 3, know all the things about SOHCAHTOA and figure out what pieces go where. So for all of these, we are assuming that the circle is at the origin, okay? So that we don't need to worry about what happens if it's not. Perfect. All right. So I want to talk a little bit about even and odd properties, okay? So those of you who are in Math 116 know that we learned about a lot of parent functions, and I've listed them all right here for you, right? All the ones we learned in 116. And at the time, like a lot of these were kind of new. We spent a lot of time talking about domain and range, and we kind of talked about even and odd, right? So we looked at even and odd parent functions, and we looked at even and odd polynomials, right? But let's revisit some of that and talk about what it means in general to be even or odd, okay? And so this was actually a question on your final exam from Math 116. One of them was like, list all the parent functions that are even. And so if we go to our list, I think folks knew that x squared was even, okay, which was excellent. I'm really glad we knew that. Which other function is even in this list of parent functions? Right, we got our x, we got absolute value of x, square root. Yeah, that absolute value was also even, okay? So those were the two even functions that we learned about before. And so let's take a look at one of those graphically, okay? So if we take a look at our x squared function, right? So let's just choose for right now the x squared. When we graphed it, we knew that there was the point 0, 0, right? What are some other nice points on the graph y equals x squared? What else? What else? What else? Yeah, we got to get that other side. So -2, 4, -1, 1, all right? And so if we looked at this graph, once we sort of connected all the dots, well, that's not bad for a Wednesday. All right, we noticed that this was symmetric about the y-axis. Okay, and so that was part of our definition of what it means to be even, is that when you reflect something about the x-axis, if it's symmetric, then you know it's even, okay? Well, let's pick some of these numbers and see if we can come up with another pattern for those, okay? So graphically, that's what it looks like. But let's pull maybe 1, 1 and -1, 1. Those are both points on the parabola, yeah? Well, another way of writing 1, 1, if we use function notation, we could say that f of 1 equals 1. And we can say that because this is our input, that 1 is this one. And when we put 1 into the x squared function, we get 1 out, right? How would I write -1, 1 in function notation? Good. F of -1 equals 1, right? And this 1 is that 1, and the -1 came from the x value, okay? So what can you tell me about f of 1 and f of -1? Like if I wanted you to compare f of 1 to f of -1, what could you tell me? Yeah, that they have the same value, right? We could also say, exactly, we could say that f of 1 equals f of negative 1. So f of 1 equals f of negative 1. Right? That's a fancy way of saying they have the same value. All right. What do you mean by that? Is f always x? Like f parentheses x? Yeah, yeah. That's like, so when we have the x in there, that's like the general equation. You can plug in any number you want, and you plug it in everywhere there's an x. Okay. Yeah, x is your input. I mean, ultimately, yeah, because you want to make sure, like when you get into Calc 3, you'll see f of y. But for what we're dealing with now and probably for the next course, is just f of x, okay? Sometimes we call it g of x or h of x. But f of x is the same as y for us right now, okay? All right, let's take a look at another pair. We had 2, 4 and -2, 4, okay? So if we write this in function notation, we could say that f of 2 equals 4 and f of -2 also equals 4, because I've got 2 as my input or -2 as my input and 4 as the output for both of those. And so can we say the same statement about f of 2 and f of -2? And yeah, we can. We can say that f of 2 equals f of -2 because they're both equal to 4, okay? So instead of sitting and saying numerically, let's do this for every single point, because that gets kind of tedious, that's the power of having an algebraic way of describing it, okay? So in Math 116, we learned that a function was even if it was symmetric about the y-axis. But what I want us to add on to that now is a function is even when f of x equals f of negative x. Okay. So what is our f of x again? We chose x squared. Okay, yes, this is for any x value, all right? So this says that the output when x goes in to the function equals the output when negative x goes into the function. Okay? So the left-hand side says, what's the output when x goes into the function? And the right-hand side says, what's the output when negative x goes into the function? Okay? So this part here is definitely more grown up than what we were looking at before, all right? But let's kind of walk through this first one. So f of x, when we look at the parabola, is just x squared. So I can replace f of x with the function, which in this case is x squared. Okay? So if I go back up to here, I had said f of x equals x squared. I'm saying that again, but just sort of vertically, f of x, and I replace it with x squared, okay? This other side says I put in negative x everywhere I see the x. That means it's not x squared, but it's going to be negative x squared. Yes, exactly, negative x squared, okay? And now we want to see, are they the same, all right? If the blue equals the purple, then we have an even function. But if the blue does not equal the purple, we do not have an even function, okay? So how do we simplify? Well, the left-hand side, there's really nothing to simplify. But the right-hand side, let's think about what we know about powers, okay? If I take a negative number and I square it, what kind of number do I get? Mm-hmm. So once I simplify the negative x squared, I get x squared. And as far as I know, x squared equals x squared. Because they're equal, we have an even function. And pretty cool, right? We don't have to pick points like we did in the numeric one. We don't even need a picture of the graph. We can just plug in the idea of a number, which is x. And then we plug in the idea of the negative number, which is negative x. Okay? So it is definitely more grown up, but it's also a lot more powerful. All right? So let's kind of walk through this process again, but with odd functions and see what the difference is, okay? So one question on your final was, tell me which functions are odd. So is this in addition to the other requirements needed to be even, or it's just another way to determine? Okay, great question. So graphically, numerically, and algebraically, all three of those show that it's even, okay? They are, you could think about it like different methods, but it's actually like this framework of graphs and numbers and equations. If you can think about every math concept in terms of graphs and numbers and equations, and you know the relationships between those, then you're in a really good place conceptually, okay? Yeah, exactly, Eric. I know, I think so too. Okay, so let's go back to the odd equations. And I think Natalia had that we had f of x equals x, x cubed, and 1 over x, right? So those were our odd functions. And let's remind ourselves how we describe them graphically in Math116. Okay, and so for this one, let's choose x squared. Let's choose x cubed. All right, it's a good one to remind ourselves what it looks like. Kind of looks something like this. Okay. And we had a few nice points on there. We had like 0, 0, 1, 1, 2, 8. And then on the other side, we had -1, 1, and -2, -8. -1, -1, -2, -8. All right? And this one, when we described it in Math116, we said this was symmetric about the x and y axis. Or some people said that was just symmetric about the origin. And both of those are accurate ways of describing it, okay? So we're almost saying to ourselves that sort of this part, when I flip it over the x-axis and also flip it over the y-axis, I should get this matching part down here. Okay, so the red part and the yellow part, because they're symmetric when you rotate them, then this is what creates that symmetry. Okay, it's a little bit harder to see, I think, than the symmetric about the y-axis, but also a way to think about whether it's odd or not. Okay. Now, numerically, let's see what happens with some of these numbers. So I'm going to pick some pairs of numbers again. We'll go with 1, 1 and -1, -1. And if we were to use function notation here, we've got f of 1 equals 1 and f of -1 equals -1. Right? Our outputs are 1 and -1, and our inputs are 1 and -1. Okay? So can we say that f of 1 equals f of -1? No, we can't, right? Which makes sense because we knew this wasn't even, so we shouldn't be able to say that. But maybe what we could say is that negative f of 1, right? What's negative f of 1?
-1.
This orange, f of 1 is 1. So negative f of 1 means take this output and make it negative. So -1, okay? If I take the 1 and then I make it negative, is it equivalent to f of -1? Yeah, because that one was also -1. Okay. And we could try the same thing with 2, 8 and 2, -8. But let's see if we can draw this conclusion with just the general idea of a number and its negative, okay? So I claim that negative f of x is equal to f of -x for all odd functions. Well, let's see. If my function is x cubed, then negative f of x would be the same as negative x cubed, right? If I want the negative of the function, I just put a negative in front of it, and then I can worry about distributing it later. F of negative x, well, that means I plug in a negative x for the x. So that's going to be negative x cubed. So let me pause right here for a moment. Are we okay with the substitutions that have been made so far? Because if we're not, we need to clarify that before we move on. Okay. So now we simplify. If I have negative and then in parentheses x cubed, well, isn't that the same as saying negative x cubed? Right? I just changed the sign of the thing inside the parentheses. And since there's only one thing, it's just negative x cubed. Well, let's think about, to simplify the purple side, let's think about how we simplified the purple side for the x, or the negative x squared, okay? So we knew that the negative x squared became an x squared because when we multiply a negative number by itself, we get a positive number. But how do we, when we multiply a negative number by itself 3 times, do we get a positive number or a negative number? Yeah, we get a negative number. So because of that, we get negative x cubed when we simplify, which is perfect because I claimed that this statement will hold true for every odd function, and those two are the same. Okay. So let me zoom back out for a moment. But what we've done is take a look at things that we used to know about what it means to be even and odd and extended it to this algebraic piece, okay? But what's going to be important for us as we move forward is that if something is even, it should follow this rule. F of x equals negative f of x. And if something is odd, it should follow this rule. Negative f of x equals negative, or f of negative x. Okay? If it doesn't follow either rule, then it's not even and it's not odd. Okay, so that is a possibility. So let's take a look at how this applies to us in trigonometry, okay? Which trig functions are even and which ones are odd? Well, what sort of apparent functions would be neither? Like the exponential, the log, the square root. Yeah. Yep, you got it. Okay, so we're gonna, no, 1 over x is odd. Yeah.
Oh, are you saying which ones are only even?
Oh, no, he was saying which ones would be neither.
Oh, okay. I thought you were just talking about the odds one.
Oh,
yeah.
no.
Okay.
All right. Okay, so let's take a look at drawing some pictures, okay? So for this first circle, we're gonna think about it in terms of sign, okay? So let's say I picked an angle, let's go with pi over 6, okay? So I know this is pi over 6. And we know this coordinate is root 3 over 2, comma 1/2, right? Now, if I said find the sine of pi over 6, you would tell me the answer is? Perfect, right? Sine of pi over 6 is 1/2. Okay. Color change. If I asked you to graph negative pi over 6, which quadrant would that be in? Good. In fact, it's just going to be down here. Okay. And what is this coordinate? Wow, you see where we're going with this? Yeah, okay. So this coordinate has the same x value as the pi over 6, but it has a negative y value, literally because it's lower than the x-axis. It's below the x-axis. So if I asked you sine of negative pi over 6, you would tell me negative 1/2, right? You go with it to the angle, you find the y value, blah, 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 -1/2. Well, what does that mean in terms of even versus odd? Okay, so we have sine of pi over 6 equals 1/2, and sine of negative pi over 6. Oh, so we have the input and the negative input, and we get a negative output. So is sine even or odd or neither? So good. It is odd. Yes, yes, yes. Okay, so here's what we have, right? If we generalize this, we don't just say pi over 6, but we call it theta for any angle, okay? Sine of theta is going to give you, negative sine of theta will equal sine of negative theta, right? Our thetas, we use pi over 6, but we could use any angle and this would be true. And one of them was a 1/2 and the other one was a negative 1/2, right? So when we change the sign of the input and it changes the sign of the output, then we have an odd function. So sine is, did I leave room for this? Okay, so sine is odd, all right? Now here's the good news. If you know sine, you also know about its reciprocal function. What is the reciprocal function of sine? Cosecant. So sine is odd, but so is cosecant. All right, so 2 for the price of 1. You got sine and you have cosecant. Okay. All right, let's take a look at tangent. And if we're talking about tangent, what else are we going to know about at the end of this? We're also going to know about cotangent, okay? So whatever we determine tangent is, cotangent is going to give us the same information, all right? So let's pick a nicer angle this time. Let's go with pi over 4, yeah? And we know this is √2 over 2 and √2 over 2. And so if I said find the tangent of pi over 4, you all would be like, it's 1. Yes, it does, right? So if you know the tangent of pi over 4 here is 1, and let's see what we get when we find tangent of negative pi over 4. Oh shoot, the numbers are similar, but tangent of negative pi over 4 is not going to give us a positive 1, but it gives us the negative 1. And that negative makes all the difference in the world. That means that, like sine, tangent is also odd. Okay? So we could even kind of say that negative tangent theta equals tangent of negative theta. Ah, you ask the best questions all the time. We're getting there in like 4 minutes, okay? Okay. All right, so we got one last pair of functions to look at. We have cosine and secant, all right? So let's pick, gosh, I don't know. This one is pi over 3. I'm only going to write the x coordinate. It's not the x coordinate. Just going to write the 1/2 and then root 3 over 2. So we know that if I said, hey, find the cosine of pi over 3, you would all be like 1/2, right? Cosine of pi over 3 is the x value there, which is 1/2. And then if we took a look at negative pi over 3, does that x value change or does it stay the same? It's going to be the same, right? The 1/2 stays the same. The y value changes, but we're looking at cosine, so I don't care about the y value. I only care about the x value for cosine. And so what we have here is that cosine of pi over 3 is equal to 1/2, but cosine of negative pi over 3 is also equal to 1/2. We can generalize this to say cosine of theta equals cosine of negative theta. And therefore, we have that cosine and secant are even function. Okay. So I hope at some point in the process of all three of these, we had a little bit of an aha moment, all right, with what it means to be even or odd, right? But let's just kind of summarize these right here in a little sentence, just because, you know, sometimes numbers make sense, but sometimes we need to write it out in words for it to make more sense, right? So the even trig functions are cosine and secant, right? These functions are even because f of x equals f of negative x, right? That's a simple, straightforward explanation, maybe a good summary of like the last 2 pages, okay? Now the odd trig functions are sine, cosecant, tangent, cotangent, whoops, cotangent, all right? And these functions are odd because negative f of x equals f of negative x, all right? So if you don't remember anything else about the last 2 pages except for this part, that's okay. This is the part where we're like, this is the rule, okay? All right. How can we summarize this? I would leave this up to you to kind of take a look at. That might be a really good way to process the notes and think about what you want to get on that reference sheet. Okay, so that's why I'm trying to ask some of these questions, like how do we summarize this? Because everyone's going to make sense of it. Okay. All right. So one answer to your question, Eric, about what is the purpose of determining if a function is even or odd is that we can use these properties to help simplify a given expression. Okay. And it's useful because sometimes we have values for a positive version of something, but we might not have the values of the negative version. So we can kind of shortcut it with the even odd there. If we know the positive version and we know that it's odd, then we know we need to change the sign to make it the negative version, okay? Whereas if it's even, we know that the outputs are gonna be the same, all right? And so let's take a look at 2 examples about what we can apply, whether something is even or odd or neither, okay? So we have this function, 2 sine x cosine x, and we want to determine if it's even, odd, or neither, all right? So one thing I find is I figure out what my f of negative x is, okay? So if f of x equals f of negative x, meaning I put in a negative x everywhere I see an x, then f of x is even, right? So that's like a good summary statement. Just another way of writing what we talked about before. So let's see if this function is even. And we'll go ahead and do that by plugging in a negative x everywhere we see the x. So f of negative x will give me 2 sine of negative x cosine of negative x, right? So all I've done here is put a negative x everywhere I see the x. But now I can use the ideas of even and odd to simplify this. So the 2 is going to stay, but is sine even or odd? It's odd. Okay, so what can I replace sine of negative x with? Negative sine x. Good. So I'm going to put that in parentheses, negative sine x. And this is just from knowing that it's odd. Okay? Now let's take a look at cosine of negative x. Now we know cosine is even. So what can we replace cosine of negative x with? Just cosine of x. Good. All right, so we've got the yellow one because it's odd, this green one because it's even, and now let's clean this up even more. I can write this as negative 2 sine x cosine x. Okay? Is this the same as my original function? And I hope the answer is no. Right? The answer is no, it's not the same because this one has a negative and the other one doesn't, right? So this function is not even because f of x does not equal f of negative x. All right, well, if it's not even, let's see if it's odd, all right? So maybe a similar statement we can write is if negative f of x equals f of negative x, then f of x is odd, right? And that's not a new concept, but it's just a different way of writing out the information that we learned in the last 2 pages, okay? So if this is true, then our function is going to be odd. Well, don't we already have f of negative x? Like we found f of negative x, right? We know that it equals negative 2 sine x cosine x. So the only thing we need to find now is negative f of x, and then we can compare it to what we found before. So negative f of x means you take the function and you slap a negative sign in front of it, and then you distribute as you need to. And so we get negative f of x equals negative 2 sine x cosine x. Oh shoot. What we got here is the same as what we got when we plugged in negative x. All right, so we have that f of x is odd because f of negative x equals negative f of x. Okay. So instead of saying, oh, I really wish we could just put this on Desmos right now and graph it, you could do it that way too. And I bet if you look at the graph, it's going to be symmetric about the origin. But another way we can do this, and we call this algebraically, is that sign is, or that this function is odd. Not necessarily, Ethan, because I would argue that sine squared x, that function, is not odd, but it has sine in it. Yeah. Okay. All right. So let's take a look at number 11 here. All right. And this will give us some of the other trig functions to look at. Okay. So remember, if we know sine, we know cosecant. And if we know cosine, we know secant. Right. So let's start by finding f of negative x. All right. Let's try find f of negative x. So if f of x equals f of negative x, then my function is even, okay? So f of negative x means, well, let's actually rewrite f of x first. I think this is a new notation we haven't really seen before, okay? So f of x, they tell us, is cosecant squared x plus secant x. Here's what this squared means, okay? This is a way of writing cosecant x, and then you square it, okay? Feel like I've gone overboard with the highlighting today. Maybe I'll just circle it. Cosecant squared x is the same as cosecant x squared. Nobody ever writes it the second way. Okay. I know. I didn't want to overwhelm everyone with all the colors though, but I secretly love it so much. Okay, so these two are the same thing, but nobody ever writes it the second way. We only write it the first way. Okay. The reason why is because you can imagine, what if I was being lazy and I didn't write parentheses? Like, what is that? Am I squaring the cosecant or am I squaring the x? Right? And so to make it clear, if I write it like this, then I'm saying cosecant of x squared. But if I want to say square the cosecant, you square the cosecant after you put the x in. Okay, so it's like an order of operations here. One of them, you take the input, you square it, and then you cosecant it. But the second one, you put the input in, and then you square it. Okay. All right, so back to our problem. We have and secant x, right? So if I want to find f of negative x, then what I'm doing is finding cosecant of negative x, and I'm squaring it, plus secant of negative x, right? So I'm looking to plug in the negative x everywhere I see the x, okay? So now let's think about this piece by piece, okay? So cosecant, is that even or odd? Right, what is cosecant, even or odd? It is odd, good. So everywhere I see cosecant negative x, I can put negative cosecant x. if I put in, so this replaced by negative cosecant x. What can I replace secant of negative x with? Right? What can I replace secant of negative x with? Is it going to be negative secant x? Is it going to be secant x? Oh, okay. So I would say let's get in the habit of writing it this way. Okay. It's not wrong to write it the other way, but we'll literally never see it. It's not even like a rationalize the denominator situation. Like I don't think that we ever see it the other way. Okay. Cool. Okay. So secant of is an even function, right? Because it goes with cosine. So we can say here that secant of negative x is just going to be secant x. All right, how do we clean up this piece? Negative cosecant, but I square that whole thing. Is that going to be positive or is it going to be negative? Yeah, it's going to be positive. So we have cosecant squared x again, okay? We're not basically removing it. I know that's what it looks like. We're using the definition of even and odd to substitute. Okay, like I know that secant of negative x equals secant of x. So everywhere I see the negative secant of negative x, I can replace it with that. Yeah, I get you. I get you. Why is it secant? Because it's even. So f of x equals f of negative x. Yeah, exactly. We're going back to the definitions and replacing it. Yeah. Okay, so because this is even, maybe that makes it easier. Because it's even, then we can replace it that way, right? And over here, because it's odd, we replace it differently. Okay, sorry, I feel like my explanations are off this week. Okay, so we get cosecant squared plus secant. Well, that's exactly the same thing as what we started with, f of x, right? F of x is cosecant squared plus secant. So we know then that f of x is even because f of x equals f of negative x. And if you know it's even, you can stop right there because if it's even, it's not odd. And if it's odd, it's not even. Okay. Well, I think, Eric, to kind of answer your question, it really sort of depends like what you're looking to specialize in with your STEM degree, you know, like I think that the applications of this vary from field to field. So part of this is understanding like even an odd graphically, algebraically, no matter what the function is. So we're just like applying an old concept to new functions. But yeah, I think that could be an interesting thing to look at for like what field you're looking for and like how does trig actually apply in that field, and I think that's going to be different for everyone. Okay, is this on the exam? Yes, this is on the exam. You will see one question that is like, tell me whether it's even, odd, or neither. Okay. All right. So we got one last section. I think we might actually make it through. Let's take a quick, just like 2-minute stretch break, and then we'll come back and finish this last piece, okay? So I'm gonna stop sharing for a moment. All right, so hopefully you were able to stretch real quick, get a quick snack, not go to the kitchen, get a snack, and then forget about it. Okay, hurry up. Oh, what kind? Oh, that sounds so good. I know, I get hungry too. Yay! Ooh. Mhm. All right, so let's finish up this section here. Gosh, I haven't had sushi in so long. Wait, what am I doing? Never? Christina, I feel like that means that people should like be offering to buy you sushi, right?
I just don't seafood, or I don't know. I should actually just go and probably like try a California roll. That's what I've been recommended.
Yeah, I think it's less like, it's not really slippery or anything like that. So if texture is a thing for you, it's not really slippery.
Oh, all right. I'll definitely try some then. I'm pretty scared, I'm not gonna lie.
Okay. All right. Yes, I know. Weirdly enough, eel is good, but I feel like mostly because the sauce is like sweet and kind of delicious. Yeah. Although sometimes when I think about it too much, I'm like, ooh, this is an eel, and then like I have a hard time eating it. All right, so last section in chapter 5. Here we go. So there are a lot of identities to come, okay? And we are starting to put together a lot of them, but I wanted to take the time here to sort of formalize them, especially in the sense of making sure that we have some of these foundational definitions down, and that we have sort of like a way to organize all of them, okay? So in the past, I've sort of put them in different boxes for students, and that's one way to organize it. If you look up online, there's a bunch of different like graphic organizers for fundamental identities, and so I would look for one that works for you, or feel free to organize it in a different way if that makes more sense to you, okay? All right, so memorizing is one part of it, but I think we actually know a lot of these more than we think we might, okay? So let's start with the reciprocal identities, all right? Let's actually start with cosecant of theta. What is cosecant theta the reciprocal of? There you go, sine. So where it says cosecant theta, I can actually write 1 over sine theta. So those are equivalent expressions. Cosecant theta equals 1 over sine theta, okay? What does that mean I could say about sine theta? It's 1 over cosecant, good. So we have 1 over cosecant theta, okay? All right, so we could kind of move along the pairs. I know that cosine is 1 over secant theta, which means that secant theta is 1 over cosine theta, right? So this name, reciprocal identities, talks about the 1 over. We're literally thinking which pairs are reciprocals. That's it. And so for tangent, we can say 1 over cotangent. And for cotangent, we can say 1 over tangent. And again, it's the one part that makes it the reciprocal identity. Okay? Make sense? Yes, no, maybe so. Yes. Okay. Now, the quotient identities, oh, what an identity means? An identity means that it's always true. Okay, so an identity means that it's always true. So this is a list of things that are always true, is really what we're looking at. And the big picture is we want to use these lists of things that are always true to show that other things are also always true. All right, what does quotient mean? Yeah, quotient means divided by, right? When we think about quotient, we think division. So you tell me, what do I divide by what to get tangent?
Sine over cosine.
You got it. Sine theta over cosine theta is tangent theta. We already knew that. Okay, but this is just a different way of organizing it and giving it a special name because it's a relationship defined by division of two functions, okay? So if tangent is sine over cosine, then cotangent must be
Cosine over sine.
okay? And so the quotient part, again, is the division of two functions, okay? So the reciprocal identities, things that are always true, the quotient relationships that are always true, those we already knew, okay? Oh, more things we already know. What a good review before testing. Okay, so odd and even, all right? So we know that some of these are odd and some of them are even, right? We had that whole sentence from earlier where we said which one was even and which one is odd. This is just another way to keep track of that information for yourself. So for example, I know that sine and cosecant are odd. So that means that sine of negative theta is negative sine theta. And cosecant of negative theta is negative cosecant theta. Okay, we just used this. Which other pair can we replace similarly to what we just did? Tangent, good. So tangent of negative theta is negative tangent theta, and cotangent is negative cotangent theta, right? All the odd ones, we just put that negative sign in the front. All the even ones simplify down to the regular function, okay? So we've got odd, and then even in the middle, right? All right, and cofunction identities. We talked about these way back when too, all right? So sine, what is sine's cofunction? Think really carefully about how things are spelled out. That tells you which ones are the cofunctions. Yeah, sine and cosine. So sine of pi over 2 minus theta is cosine of theta. And cosine of pi over 2 minus theta is sine theta. Okay. I could do the same thing with tangent and cotangent. And I can do the same thing with secant and cosecant. You got it. Okay. All right. So this was a good summary of sort of like the ones that we already knew, but we just didn't formally say these are called identity. All right. But one thing that is new for us is something called the Pythagorean identity. Okay. Now there are 3 Pythagorean identities. One of them I think is so important to commit to memory. The other 2, I will show you how to get it from that one that you choose to memorize. Okay. So instead of memorizing 3, memorize 1 and figure out how to get to the other 2. So in the unit circle, this is 1, right? This side is our cosine, and this side is our sine theta, right? We buy that? We have a right triangle. We know that the vertical distance is sine and that the horizontal distance is cosine, right? Now we know this is a right triangle. So it's fair to say that one side squared plus the other side squared equals 1 squared, or 1. Right? Because all I'm doing is saying a squared plus b squared equals c squared. The Pythagorean identity also applies when we think about it in the context of the unit circle. Okay? Yes, Eric, that's a really great summary. So sine and cosine are only equal to the side lengths when the hypotenuse is 1. Exactly. Okay. If we weren't in the unit circle, then we couldn't say that. Right? Okay. So we're going to take this Pythagorean identity. This is the one that I think is important to memorize. Sine squared plus cosine squared equals 1. Okay? But now I'm going to say we're going to do 2 things. Okay? So first, we're going to divide every single term by sine squared. So what I mean by that is we have sine squared theta divided by sine squared theta plus cosine squared theta divided by sine squared theta, which equals 1 over sine squared theta. How do you know he didn't start all of this? All right, let's simplify. What's sine squared divided by sine squared? 1, you got it. So that first term goes to 1. What's cosine squared divided by sine squared?
Cotangent, right?
Cotangent, but they're both squared.
Cotangent squared?
Yeah, you got it. You got it.
It's smart.
So cosine divided by sine is cotangent, but they're both squared, so it's going to be cotangent squared. Okay. What's 1 over sine squared then? Close, it's not cosecant. But it's going to be cosecant squared. Yeah. Okay. So why did we divide by sine squared? Oh, you're totally fine. Why did we divide by sine squared? To get the other Pythagorean identity. Which sounds kind of silly, but that's where the other Pythagorean identity comes from. Okay? So sometimes it'll be useful if we're looking at problems to make a substitution using cosecant and cotangent rather than sine and cosine. Okay? All right, we're gonna go back to that original one. Sine squared plus cosine squared equals 1. This time, instead of dividing by sine squared, I'm gonna have us divide by cosine squared. So what that means is we have sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. Okay? I'll give you a moment to try and simplify this one on your own. And then let's maybe share out some thoughts on what we think it simplifies to. I'm fine, I just swallowed water the wrong way. Thank you. One of my professors was like coughing a lot in his video. And I was watching the video, but I was like, oh my gosh, please don't have COVID. I was like, I really need you to finish this semester of teaching. He's fine though. I think he just has a little bit of a scratchy throat. All right, so what can we simplify here? What can we simplify the sine squared divided by cosine squared to? Whoa, there we go. Tangent squared, right? Tangent squared, because sine squared divided by cosine squared is tangent, and they're both squared, so it's tangent squared. Plus, well, that goes to 1. And 1 over cosine squared is exactly what Eric said, secant squared theta. Okay? So, I would make sure that we know all of them, okay? I would put a lot of pink stars around this one because I think this one is probably the most important one to remember. Not just because you can get the other 2 from it by dividing cleverly, okay? So if you divide this, you will get this one. And if you divide by the cosine squared, you get the tangent and secant one, okay? But also, when we start to use it in, I'm gonna say a bad word, proofs. When we start using them in proofs, the one with the pink stars comes up pretty frequently. So it's a good substitution to know, because you might be in the middle of a problem. You might be in the middle of a problem and it looks so long and gross, but there's a sine squared plus cosine squared, and guess what you can substitute for it? A 1. Or you might get to a problem and it says 1 plus cotangent squared, and you could replace that whole thing with cosecant squared, right? So it's like, what other ways can we say things to make our lives a little bit easier, right? That's really where we're going with these proofs. Right? So in these last few moments, let's take a look at these 4 examples, okay? I happen to love simplifying identities and things like that. So for better or for worse, I really like doing these kinds of problems. I find it very satisfying that you can basically turn something that looks complicated into something that looks way more simple, okay? I find a lot of beauty in that. How much do you really need it, like in your real life? I mean, probably not a lot, but you know, I think it is very satisfying in a different way than when we work with only numbers, okay? All right, so let's take a look at example 12, right? We have secant theta over tangent theta. Yeah, so when we're looking at these, we're assuming that we're working with all the trig relationships, okay? Good question. All right, so Natalia, 1 over cosine theta. Beautiful. So she used the reciprocal identity there, right? The reciprocal of secant is 1 over cosine. And then she used the quotient identity for the bottom. So reciprocal quotient. Oh, hey, we have that sandwich thing we talked about earlier. 1 times cosine theta makes my numerator, and sine theta times cosine theta makes the denominator. Let's reduce. How can we write this by a single trig function? You got it. So when someone says secant theta divided by tangent theta, it's really like a dressed up version of cosecant theta. They are the same thing, okay? Yeah, and Eric, the sandwich method is just like a shortcut way of thinking about how to divide by fractions, so you don't have to write out like times the reciprocal, but it's basically the same thing. Okay. Secant theta over tangent theta is not on our list of identities, but we could say that secant theta over tangent theta equals cosecant theta is an identity. Yeah. No, I don't think I asked you to explain the identities on this exam. Okay, so let's take a look at example 13, okay? So I have tangent theta times cosine theta. Well, let's see, tangent theta, well, I could write that as sine theta over cosine theta, right? And then how can I write cosine theta as a fraction? Like, what's the easiest way to write cosine fraction? Yeah, cosine theta over 1. Well, check this out. These reduce. So tangent theta cosine theta is a really fancy way of saying sine theta. Does that make sense? So we're kind of making substitutions from the list that we had and trying to get it into a more simple form, okay? One thing I want to highlight with these two is that one good strategy to sort of keep in our back pocket is to change all terms into things with sine and cosine. So do you see how for the number 12, Natalia changed secant into 1 over cosine, and she changed tangent into sine over cosine? That's what I mean by changing everything into sine and cosine. That's like a good strategy to think about, to have in your toolbox, okay? And we kind of use the same thing for example 13, where we changed tangent into sine and cosine, but we didn't change cosine because it was already cosine, right? That's probably one of the top sort of things that make your life harder with identities, is you try and change everything, but sometimes you need to change like one thing and see how everything else goes before you start changing other things. Yeah, if you've never done trig proofs before, I'm really trying to set the stage for a lot of chapter 7 right now, okay? All right, so let's take a look at these last 2 questions here, okay? So sometimes if we don't know what else to do, we change everything to sine and cosine, and that's not bad, right? Now, in this case, in example 14, if we were to use that strategy, what would we change to sine and cosine? For sure. So I have sort of this cosine of pi over 2 minus theta, and I have this cotangent. So are there any parts that I want to change to a sine and cosine situation?
Cotangent part 2.
Exactly.
Cosine over sine.
So with the cotangent, right, we can change that to cosine over sine. So let's keep the first part by itself right now, or as itself, and then we'll change cotangent to cosine theta over sine theta, okay? But, so that makes this part better, but what can we replace this one with? Right, so that's like a good time to go back and look at that page with all of the different identities on it. This is a cofunction identity. Right, so everywhere we see cosine of pi over 2 minus theta, I can change that into sine theta. And I just put it over 1 because I knew I was going to multiply it by another fraction. And, oh, those cancel. Pretty cool. I wrote this in this super complicated way, but another way I could have written it was cosine of theta. That's it. Okay. All right, we got 30 seconds for this last question. Okay, so let's do this. Yeah, so I split it into 2 fractions. So I just like sort of grouped the numerators, and then I grouped the denominator. Okay. How else can I write sine of negative theta? Which identity was that? That was our even, odd identities. Exactly. So because it's an odd function, I can replace it with negative sine theta. All right, well, cosine theta, I'll just keep that because one strategy that we've learned so far is change everything to sine and cosine, and that's already like cosine. All right, how could I write tangent theta, or 1 over tangent theta in terms of sine and cosine? One over tangent is cotangent, right? And cotangent is cosine over sine. Good thinking. All right, does anything reduce? Sure does. And so I end up with a negative cosine squared theta. So this big fancy expression in the beginning is equal to negative cosine squared theta. Right? So that's really what we're trying to do. You can think about sort of these kinds of questions as ways to practice making substitutions from that list. That's one thing that we're practicing. But the other thing we're practicing is our logical reasoning. Like, what kind of things make sense? What's the most efficient way to accomplish that? Okay. So I know we are over time, so I'm going to stop the recording right here. But a couple of things I just wanted to mention before you all leave, which is I know that Val has a tutoring session today, so hopefully that will be helpful for you all. Okay. I did want to also remind you that I am available via email and things like that if you have questions about any of the stuff. Okay. I love how much as a group you are working to figure out like, okay, like how can we solve this on our own? But it's also totally fair game to like just send me an email and say, hey, can you clarify this for us? I might not respond like immediately, but I'm usually pretty good about emails. So, you know, if you have questions as you all are studying for the test that opens on Friday, don't feel bad about sending me an email. Like I think someone sent me an email with a picture of their work, and I was able to just like, you know, go through the work, show them where they went wrong, and then get that right back to them, right? So just because I don't see you face to face doesn't mean I can't still help you out and give you feedback on things if you need, all right? Okay, any questions before we take off?
I have one, it's very small, but can you go back to number 12? I'm just curious, as it's not a big deal because like I understand it, but I'm just wondering why you wrote number 12 that way when you were multiplying by the reciprocal. It was like our second to last step.
Yeah. Why did I write it as 1 over sine?
1 over sine, yeah, because I wrote, because it ends up being the same thing, but I wrote 1 over cosine times cosine over sine. It doesn't matter because you multiply across and you get the same thing, but I was just wondering if there was a reason as to why you did that or no.
Like why wait, sorry, say that again?
Okay, so typically when you have a fraction divided by a fraction, you would multiply it by the reciprocal of the second fraction, right?
Yeah.
Yeah, so when I did that, it was 1 over cosine times cosine over sine, but you did 1 over sine times cosine over cosine. I mean, when you multiply across, you get the same thing. I was just wondering.
Oh, so just, because these are multiplied, it doesn't matter whether I write sine first or cosine first?
Right.
Yeah.
Okay. So they're just saying, okay, I was wondering if there's a particular reason or anything, but okay, thank you.
Nope, just the commutative properties of multiplication.
Okay, thank you. Yeah.
All right. Alrighty, folks.